Nuclear energy started from the desire to take the power of the atom and make a bomb. Now, nuclear energy is being used to solve the climate issue that we have with carbon emissions. We can use nuclear power to make carbon-free electricity on a grand scale never seen before. I've got almost 4 decades in the energy sector. Come with me as we take a look, an honest look, at nuclear power. Welcome to Climate Honesty, where we simplify complex topics to help you be better informed on energy and climate. We are often afraid of things that we don't understand. That is definitely the case with nuclear. Most people don't really understand even how nuclear works, but we're surrounded by nuclear reactions all the time. The sun is a nuclear reactor, and we receive radiation and heat and energy from the sun every day. Nuclear energy is actually the energy that holds matter together, and if we simply tap into it, we have an unlimited supply of energy. It is carbon-free and produces way less waste than any other form of electricity generation by far, and can provide enough power to power the entire world as it stands today and in the future if our power demands significantly increase. It is also one of the safest forms of electricity generation statistically. However, we're human beings and we don't always operate off statistics. We operate off of how we feel about something. Nuclear's been around now for about 70 years. So we have a lot of information about how well it's performed. How safe is it? How much does it cost? What kind of reliability issues do we have? And we can really take an honest look at nuclear power as a potential source for the future. First, I'd like to show you a website that looks at something called carbon intensity, and it simply is a measure of the CO2 emissions per kilowatt hour of electricity generated for a country or a region. And it's really kind of eye-opening to see countries that have embraced nuclear and countries that have not embraced nuclear and see what the difference is in their carbon emissions. Here is a map of Europe showing carbon intensity, or the grams of CO2 per kilowatt hour. And we can see that France has very low emissions. The green is low and the dark brown is the highest. So going from green to brown is a function of the increase in carbon intensity. Now we can see here that France at 29 grams is very low, and we can also see that most of their power comes from nuclear. Now here's Germany, and Germany has a high percentage of renewables, as much as 60%, but they also use a lot of coal, and their emissions are 12 times or more what France's are, and they have no nuclear. Next, we look at Spain, and they have about half the emissions of Germany, even less than that, and they have a substantial portion of nuclear and a fair amount of wind, and they use gas and very little coal. That's why their emissions are so much lower. Now, Italy is a little bit less than Germany, and they have a large percentage of gas and not near as much coal and not near as much renewables as well. Now, this is interesting. With the U.S., we have less carbon emissions than Germany does, and we only have 20% renewables versus 60% renewables because we're using gas instead of coal. It just goes to show you that going all in on renewables does not necessarily mean that your carbon emissions are going to go down significantly. If you're interested, I would encourage you to go to this website and see how carbon, or rather electricity generation, and carbon are related. When we look at the carbon emissions from the countries that have embraced gas and nuclear, they have lower emissions than those that are continuing to use coal. Even the countries that have a significant portion of what we call renewable, of wind and solar, they still have high emissions if they continue to use coal. It's only when they embrace gas or they embrace nuclear at a large scale that their emissions go down. It's obvious from the data that if we were to embrace nuclear on a large scale, both in the United States and around the world, we would significantly reduce carbon emissions. If we're going to embrace nuclear on a grand scale, there's 3 issues that we have to deal with, and they're more perception than they are reality. Number 1 is the waste and its safety, the safety of operating the plant, and the cost. In order to address the safety issue, we really need to understand how a nuclear reactor works and what makes it safe or not safe. About 80% of the reactors in operation today are a pressurized water reactor. And what that means is that water flows through the reactor and is what transfers the energy from the reaction to a heat exchanger to make steam that drives a turbine. So what is a reactor? Well, all the reactors in service today are fission reactors. And fission is simply the process of breaking apart a nucleus and using the energy that's left over to do some form of work. If you remember from high school chemistry, our atoms are made up of protons, neutrons, and electrons. Now, if I was to split a uranium atom, which is at the high end of the periodic table, I end up with two atoms that require fewer neutrons to match their protons. And this is where the excess neutrons come from. Those excess neutrons have a lot of energy. As we've learned from Einstein's E = mc squared, the mass of the neutron is converted to energy in this process. This excess energy then is transferred to whatever fluid is flowing around the fuel rods. So when a neutron is released from the atom in my reaction, in order for me to continue a chain reaction and have it hit other atoms and create more neutrons, I need to slow the neutron down. When the neutron hits another atom and splits it, that's called fission. So when the neutron hits an atom, it has three choices. It can either be absorbed by the atom, it can cause fission, or it can bounce off. A nuclear reactor operates by controlling these three factors: the absorption, the moderation or thermalization, and the fission material. A nuclear reactor core consists of these three elements. We've got the fuel, which is the fissionable material, typically uranium, and we've got the moderator, which is there to slow the neutrons down, and that is typically water. And then we've got the control rods, which act like absorbers. And that is going to be cadmium or boron or hafnium or some material that absorbs neutrons really well. And so that's there. If we need to stop the reaction, we can insert the control rods, and that will absorb all the spare neutrons, and it'll make the reaction stop. One of the beauties of the pressurized water reactor is that it's inherently self-limiting, meaning that if the water evaporates due to being overheated, then it will stop the reaction because it doesn't have the moderator and the neutrons are traveling too fast. If the neutrons are traveling really fast, then they will not be able to cause fission by hitting other neutrons. Using this concept of how a reactor works, let's talk about safety. In 3 Mile Island, there was a situation where the water came out of the reactor and the reactor actually shut down. It did overheat inside the reactor and had a meltdown, but it only melted some of the material inside the reactor. And the reactor's designed with very, very thick steel, like 8 inches thick steel, and then a concrete dome around that. So even though the reaction got very hot and melted some of the steel, it never lost containment. And so 3 Mile Island really wasn't a disaster. It was a failure of the control system and the processes that were used to control it, not nuclear power as an unsafe form of energy. 3 Mile Island was actually designed to handle such an event where the loss of water would happen and the reaction would slow down and eventually stop. And is exactly what happened, despite what nuclear activists claimed. 3 Mile Island was the only disaster where nobody was injured and no radiation was leaked. In spite of the fact that no radiation was leaked and nobody was injured, 3 Mile Island had a major impact on nuclear power in the United States. Fukushima was a much more serious accident where the plant was hit by 50-foot waves that knocked out emergency power and grid power, and 3 of the reactors completely melted down. However, 28,000 people were killed due to the tsunami and the waves, but nobody was killed due to radiation. The Chernobyl accident in 1986 is by far the worst nuclear accident we've had to date. Now, its reactor is not inherently self-limiting like the pressurized water reactor. They used graphite as the moderator. So when it overheated, the graphite actually caught on fire. The overheating caused overpressure of the reactor and they lost containment. And then it was the burning graphite that released all the radioactive material that caused the problems. In addition, there was no containment dome over the reactor in case of a meltdown. And this is how the material got released into the atmosphere. Had there been a containment dome, there would have been no release of radioactive material. The most exaggerated estimates put the death toll for Chernobyl at about 4,000 deaths. What we learned from Chernobyl is that inherently safe designs are absolutely required for nuclear reactors, but really what failed was the Soviet system and the emphasis on power output over safety. These accidents, along with the association of nuclear power with nuclear weapons, have given nuclear power a really bad reputation, in addition to all the anti-nuclear activists that have put out tons of false information about nuclear power and nuclear exposure. There have been almost as many deaths associated with Chernobyl by the installation of wind turbines. If you look at the data on industrial accidents in installation of wind turbines, it is close to the amount of people that we lost in Chernobyl. And this is not insignificant. The same thing is true with solar cells. I know personally 3 people that died in a plant I was working in due to a leak. I've known the same thing is true in oil and gas. There is accidents that happen all the time. And this is just the reality of the world we live in. In the United States alone, we lose 46,000 people a year driving vehicles, yet every one of us jumps in a car every day and goes to work or does what we need to do with our car. When we compare the risks associated with nuclear power to any other form of electricity generation, nuclear power is the safest form of electricity. I realize that's a pretty bold claim, and that saying it does not make it true. I'm going to make another video and we're going to go through the safety in more depth, and we're going to go through the anti-nuclear propaganda that has been foisted on people and try to debunk some of those claims and come to a conclusion that's honest about what the actual risks associated with nuclear power are. The other issue we have not talked about yet is nuclear waste. Now, I was against nuclear for a long time because I thought the waste was an issue that we couldn't solve. But that's not actually true. We have ways to store the waste very safely and for extended periods of time. And there's no reason why the nuclear waste should stop us from nuclear power. Because if we look at all the other forms of electricity generation, we end up with tons of coal waste. We end up with tons of solar panel waste and all the toxic chemicals that go along with making solar panels. The same is true of wind turbines. We have wind turbine blades piling up right now, and we have lots of waste to deal with no matter what form of electricity generation we have. But if we compare nuclear waste, so the waste of all the other forms of electricity generation, nuclear waste is actually a whole lot less, significantly, orders of magnitude less. And it is a problem we have solved. So again, we'll talk about nuclear waste in another video, and we'll dive into exactly what we do now with all the nuclear waste and how much has been generated and all those types of issues. Well, what about the cost? Now, the cost of nuclear power in the US went up substantially due to overregulation and changing of regulations in the middle of construction projects. As anybody who's worked on construction, if you change the design midstream, it costs a lot more money. Now, in most countries around the world, it takes 4 or 5 years to build a nuclear power plant. In the United States, it's up to about 16 years to build one due to all the regulations that are burdening the system. So if we're going to keep the costs at a reasonable amount, maintain the safety, we've got to reform how we manage nuclear power plants. If we think back to when nuclear power started, the first reactor was built in 3 years. There's simply no reason that a power plant should take as long as it takes to build. The only reason it's happening is because there's people in power that are anti-nuclear, and so they do everything they can to put roadblocks in the way of people getting things done. All this does in the end is make it harder to solve the issue of going to a low-carbon power generation system. And I think people are starting to wake up to the fact that in order to go to a truly low-carbon or carbon-free electricity generation in the future, Nuclear power is really the only viable option that doesn't have all the negative consequences that go with wind and solar and batteries. Like and subscribe if you enjoyed the video. Check out my channel for a deeper dive into the topics of energy and climate change.